Now let's define what a field is by seeing the motivation for learning fields. A field is a set K, not just a set, a non-empty set, together with two operations, addition and scalar multiplication. We saw that we wanted to be able to add the arrows, we wanted to scale them. So the scalars belong to this set, non-empty set, which we call field. We want closure in the sense that if you pick two scalars, R and S in this set K, and you add them, you want to still get a scalar in this set K, which means that when we're looking at the arrows, when we were adding fractions of arrows to the other, you want to get another fraction or number which is still in the set K. But it could happen that you could have three or more scalars RSP that you want to add. Now you can only add two at a time. So you can either add the first two and then your last scalar P, or the last two and the first. Now you want that irrespective of the order, you want it to be the same. And the equality here is what we call the associative property. But we wanted a notion of doing nothing. In this sense, the identity and the addition, where when you add and you reverse, you want it to be the same. So under addition, you want this unique element 0, which we refer to as the identity element, such that for every element R in your set K, if you add R to this identity 0, it does nothing to it. You still get back your R. Whether you add it from the right or from the left, it still remains the same. That's what we call the additive identity. But we wanted a notion of reversing direction. So if you had your arrow in this direction, you wanted to reverse it in the other direction, where we had the positive and the negative direction. So for every scalar, we want its reverse or its inverse or negative to belong to the set K. And that means that for every element R, you want its reverse, which we call negative R, to belong to it, so that if you take that number and you reverse it again, it means that you did nothing, okay? Whether you started with the reverse first or the number itself, it still results in nothing. Now, if you have your set, non-empty set K satisfying all these four, but in addition, we want that the order in which we add our arrows not to matter. So that if we have our scalars R and S, we can choose to add R before S or S before R. We want the order to remain the same. And in math, we call that a commutative property. So if for your non-empty set K under addition, if all these 5 axioms of closure, associativity, additive identity, additive inverse, and commutativity is satisfied, then we say that your set K under addition is an abelian group. Now, if we consider the second operation of scalar multiplication, if you can now consider your non-empty set K, but now we are omitting the 0 element, the do nothing element, then we want that if we multiply any two scalars, we still get a scalar. So you want a closure under multiplication, but you also want associativity because you could have 3 or more scalars that you are multiplying. And you don't want it to matter whether you multiply the first 2 scalars before you multiply the third, or the last 2 scalars before you multiply the first. You want it to be the same, and that's called the associativity and the multiplication. But you also want a notion of doing nothing when you are multiplying a scalar. So you want a unique multiplicative identity 1 belonging to your set, such that if you multiply any element in your set out by it, whether from the left or the right, it leaves the elements the same. But we wanted a notion of what? Inverse, in the sense that the scalars that we had, we wanted to find fractions of these scalars. So fractions in the sense that you want to find multiplicative inverses, so that if you have any scalar, you have another scalar, which is the inverse of it. Or you can think of the reciprocal or the fraction of it, so that if you multiply that scalar by its inverse, it gives you back your your multiplicative identity, whether you multiply it from the left or from the right. And finally, you want that your multiplication to be commutative, so it doesn't matter the order in which you multiply. So for all scalars, R times S the same as S times R. So that means that your set K, if you take out your 0 element, and the multiplication is an abelian group. So a field, in summary, a field has what? 2 properties, right? A field K is just what? You have a set, non-empty set K together with two operations, so that's what you have what? An abelian group, and the addition. And also you have an abelian group and the multiplication, of course, if you omit your zero elements and the multiplication. Okay. Yeah, note that you have to omit the zero element in your field. Okay. So that's what a field is.